I'm going to get Maxim going here fairly quickly because he was asking me about the timer very quickly, which means he has a lot to cover. And it's a super important topic about supply chain attacks because if the robots don't get us, this shit will. Have a wonderful time.
Thank you.
Let's give him a big round of applause and a big welcome.
Thank you. Imagine one sunny morning, you read the news, a crypto worm disrupts operations of hundreds of companies around the world and government networks of 25 countries. The worm is spreading, and the initial blast radius is estimated to be around 28,000 machines, and now likely affecting much more computers around the planet. Security industry struggle to understand, how did this happen? There is no one source of compromise. Eventually, a security researcher with support from cloud providers connect all the dots and find the source. All backdoor software were pulled from cloud buckets that were abandoned in the past and reclaimed by the threat actor. The risk many researchers has raised in the past materialized on the truly gigantic scale. The buckets is taken down by the cloud provider with estimates suggesting like about 5,000 buckets being affected. This is not real incident. It was me who claimed 5,000 buckets, and those are images of a fake news channel generated with LLM. But the risk is very real, and today I want to invite you on a journey to dissect the anatomy of such an attack and talk about root cause remediation. My name is Max. I am security researcher and engineer at Big Tech, mostly doing red teaming these days. I have PhD in computer security. I presented at this stage twice in the past, and I open sourced a couple of projects for fuzzing, for software analysis, and for GCP scanning. So the talk will be logically divided into 5 parts. We're gonna try to understand the motivation of supply chain attack via S3 buckets. We will discuss how an attacker equipped with modern elements of big data analysis and LLMs can bring those attacks on a really giant scale. We're gonna walk through 9 case studies, and then we're gonna talk about root cause remediation here. Before we start, I need to say that I'm presenting on my own behalf. This presentation does not reflect opinion of any of my past or current employers. So why do we want a supply chain attack in the first place? So if you've ever done red teaming on pen tests, you know that perimeter penetration might be really hard. And then as an attacker, you might notice, right, that attack cost grow as long as you want a higher efficiency. And you kind of want to invert this game, right, in your advantage. And in my opinion, supply chain attack give you that advantage. The attack surface usually grow with the size of the company. Depending on the software, you can actually end up in privileged parts of network or even in prod, right? And the obvious disadvantage is precision, right? You have to target something that's used by your target, or maybe you don't care, or maybe you compromise something that's used by anyone. So there's benefit. How does it work in practice in case of cloud buckets? So let's say you have something that's running on a potential victim's machine and pull executable code from a cloud bucket. It can be an automated job, or users just follow some instruction, let's say curl and pipe it into bash. What's going to happen if bucket is deleted? Well, users will get 404 from AWS, right? But the bucket namespace is available. So someone like with bad intent can claim the bucket, put malware into it, make it public, and well, everyone who rely on that bucket will get infected, right? Same is actually applicable to malware. Imagine you have a host compromised with stage 1 that's pulling stage 2 from S3 bucket. Someone sends abuse report to cloud provider, the bucket is taken down, and at some point recycled back to consumers. An attacker who is not affiliated with the original malware, right, can claim this bucket, and again, put malware into it, enable public access to it, and, well, infect all the victims of that malware. And In general, this risk is not something that's unknown to the industry, right? Real threat actors and security researchers have been abusing and showed that risk in the past. For example, like backdooring Python packages, targeting AWS S3 buckets, expired domains, popular NPM packages, and even top-level domains of a sovereign state, right? And it was also presented at this stage, at DEF CON. People were hacking software, and 2 years ago, Thomas Johansson presented the danger of expired TLD domain, well, to pawn internet. So there's a risk. And as for malware, this Watchtower research is quite cool. They showed that it's possible to hijack a lot of expired domains in web shells with backdoors, where backdoor phones back to those expired domains. So check it out, it's quite cool. And the closest work to this one is this another great Watchtower research where they claimed 150 buckets and also showed the risk, right? They published it when I was wrapping up like the first batch of my research here, but still. We have still a lot of remaining unknowns here, right? What is the real scale of the attack? What if we claim a lot of buckets, right? What would be impact? Can we actually simulate it and see how it works? Because, well, in theory, everything works, right? Supply chain, but in practice, there are a bunch of caveats, right? And, well, it was true in this research. I had a lot of buckets that I initially thought are exploitable, they were not. And, well, what about data? We will have a lot of data, right? You will see it. And how do you navigate this data? What is the true cost of attack? And actually, no one talk about root cause remediation here. We're gonna close these gaps today. We also have to be very careful. There are certain rules of engagement here. First of all, buckets always has to stay private, right? We always return 403. We don't want like compromise actual people. If we want to test anything, we test it on a clone of the bucket. We respect user privacy. We don't attribute to individual IPs, individual organization. I want to show you like the scale and the big picture here. And we also responsibly disclose the findings later about that. And our approach is quite simple. We search for buckets, we check if it's available, we claim it, we enable logs for 5 days, we triage logs to find sensitive stuff, we evaluate security impact, and, well, I guess profit. Let's move to the part where we search for the buckets. The best place to store your code these days is GitHub, right? It's petabytes of data, millions of repositories. And unfortunately, they don't kind of allow you to search through all the code, right? You cannot just query it. What really enabled this nice tool called Source Graph, right? Search engine. It allows you to search GitHub just in seconds, right? And now all you need to do is to search for s3.amazon.aws.com or S3, right? And you get everything. And then you extract bucket names with this like ugly regular expression, and that's it. And you can say apply same for Maven and PyPy, where you have millions of files. You need to list and fetch repos from repo1 or PyPy. That you like download package, you extract it in memory, you apply these regeps, and well, you have buckets. The only difference here that in case of GitHub, it was seconds. In Maven and PyPy, it was 1.5 months running on like machine on my wife's computer. It was super noisy, a lot of CPUs. Eventually, it lost power, so I gave up. Like, okay, I don't want to run it anymore. But eventually, like, I think I managed to crawl through like 40 or 45% of everything there. Anyway, for malware, it's even more challenging, right? You cannot just get all malware. And I was pretending to be a lazy and, well, since lazy and poor hacker in this research. So it was impossible for me to get all the samples. And even if I would get them, there was still a problem, right? Malware is usually packed and obfuscated. You need to probably run it in sandbox, and it opens the whole another layer of problems, right? But then this nice resource called URL host, I found it, and yeah, it was relatively straightforward. They allow you to get all links to Amazon AWS, right? So it was perfect for me. Okay, I'm pretty sure you are interested what I got. For PyPy and Maven, I registered 480 buckets, 255 received traffic, 4.5 million requests, and 3.5 gigabyte of logs. This is the geography of requests, right? 15,000 hosts, 129 countries. For malware, I got like 188 buckets, 175 received traffic, 2 million requests, almost 4 gigabytes of logs, and this is the geography. So it's 20,000 hosts from 142 countries, and they were mostly pulling executables and JavaScript, right? As for GitHub, there we got 4.5 thousand buckets, 1.5 received traffic, almost 4 million requests, and 19 gigabytes of logs. So it was quite a lot. And this is the geography. So it's 243,000 hosts, all countries except probably North Korea, right? But keep in mind that most of those requests are not sensitive. They might not be dangerous in the first place, right? So how do we find dangerous out of this noise? And well, let me show you. This is an example of a log query to AWS, a lot of fields, but what we really care about is bucket name, IP address, request type, object URI, referrer, and user agent, right? This data allow you to get like the context around request. But still, we had 26 gigabytes of logs and 11 million requests. So it's a lot, right? And I needed to navigate through it. But a lot of those requests are coming to pull non-sensitive stuff, such as pictures, videos, some text files, like training data, and so on. You can just remove it, right? We can also filter out like bots, scanners. You know, there are a lot of bots these days that try to scrape everything for LLM training. You can like remove it. You can also aggregate per unique IP, right? If someone pulling something in a loop, we count it as in one host, right? And still, I had a lot of requests. Probably 3 years ago, I would just give up or look through them manually. But these days, we have LLM agents that can help to do the classification for you. So I leveraged the custom LLM agents to classify requests, and I got like, I guess, time saving from like a month to a couple of days, from like gigabytes of logs to a few megabytes with 500 sensitive buckets. Of course, I had like hallucinations and like when LLMs was simply wrong, but still, it kind of worked. If you're curious about LLM, this is the architecture, right? You have 3 components working together. One element is a planner, aggregator, classifier. I give tools like internet search and GitHub search for the agent, and I save answers to database, right? And so this is like the prompt, right? You provide the bucket name, you provide actual requests, it like construct a plan, then in the aggregator with the tools, right, it actually query and pulls all the content, and then with all this context, the classifier makes the final decision. This is how it looks in practice, right? That ugly web page, right, with a lot of context, and this is an example of LLM like telling me that, well, something is trying to pull Minecraft-py from assets.minecraft.net, unpacking it, and well, classification is executable because I know that on the website they ask users to execute it. So yeah, a big time saver. All right, so let's talk about results. Before we show examples, those are the sensitive types that I came up with. So it's executables, ML models, archived with executables, PyPy Maven packages. I had dynamic web content, static sensitive files, configs, and data write attempts. So let's start with examples on executables, right? So statistics were dominated by PyTorch and Microsoft executables and archives as executables. For SN statistics, mostly ISPs, so like end users, right? I had requests from like universities, maybe students on campus, maybe administrative network, you never know. And I had a lot of like business entities, like small, medium business, and a large stock trading company. A canonical example would be this large network equipment company who used to serve installation binary from 3-bucket. They changed the distribution policy, made an announcement, and deleted the bucket. But unfortunately, the link was still used by a lot of clients not affiliated to the original tool owner, right? Like this one, like a PowerShell script where they pull and execute a binary from the bucket. And in this case, it's 162 hosts who would get execute our malicious code. And another example is Minecraft, right? It can be played on Raspberry Pi, and you need to download, the website was referencing the package that you need to download and unpack and execute from, again, an S3 bucket, and S3 bucket was abandoned. And well, again, this gives us a very straightforward to get code execution on a lot of hosts. We also had a lot of requests to pull vagrants.box VMs, right, from abandoned S3 buckets. You can obviously put backdoor in VM, but escaping VM is not an easy job, right? How about executing code on the host? And it's also possible because vagrant allow you to put like system command in the config, and anytime user like download the box and add it, not like execute, even add, you can execute your code. So very straightforward way to get code execution, right? Now, PyTorch models. A quarter of requests came to pull PyTorch models, right? And they allow arbitrary code execution because they support, like, PyTorch relies on pickle deserialization to load models, right? And, well, it's pickle deserialization allow you arbitrary code execution by design, right? They put some controls in place, but not everyone rely on them. Right, and let me show how it works in practice. Hopefully the demo will work. Okay, so we have this open source project, right? Super gradients, 4,000 stars. They used to serve pre-built models from like S3 buckets, right? And then they change it, but people who rely on the old ones still were vulnerable. And you can see like one example. We are going to use this one in this demonstration, right? So we go back. This is just a simple script on how to load this model, right? All it does, it load it. And if we execute it, right, you will see 403 with the attempt to pull it from the bucket. So this is 403, right? If you scroll it up, you see the attempt to download it from the bucket. And this is the package, right, the old version to show in the demo. It's like 2 years ago, right? I need to apply patch. As you remember, we don't want to run it on like actual bucket. We want a clone. So this is the only way you can simulate it safely, right? So this is the change. Like just 2 places, we add this random string to the bucket name, right, and claim that bucket. And we can scroll down, and that's basically another one. So we patch it, and now we can go back. If we run it again, just to validate, right, you're gonna see the attempt to pull the model from the copy of that bucket, right? Okay, so now let's poison the model, right? We're gonna rely on this code snippet from Snook, right? It's a minimal implementation to inject code in PyTorch. Relatively straightforward. We just import to sos.system calculator. So that's basically it. And we save it in the PTH file, right? All right, so let's close it. So we're gonna poison this model, right, that I downloaded from there, like new place. Okay, so we have the model. Now we need to reconstruct the folder structure the tool expect, right? The open source super gradients. And now we are ready to upload it to S3 bucket, right? So this is the name of the bucket, right? So we upload it. We need to upload folder, not file, right? So we go back. We upload it. So the model is 34 megabytes. Right? And all you need is just to enable access to it, right? Well, world access. Okay, so we upload it. And now we can pull the model, like just rerun the script, right? And we will get a calculator. So the model is loading, and we got this ugly full screen calculator. Okay, now let's move to another example. I had even bigger open source project with 33,000 stars. Again, same problem there, right? People who rely on old bucket got compromised, right? And in this case, you can again poison PyTorch model and get code execution when people load their like weights, right? All right, so let's go to Maven and PyPy packages. Out of hundreds of buckets, I actually got only 9 sensitive buckets, right? Still like 3.8 thousand IPs, JavaScript, and executables. I want to show you one example that is not so clean, I think. The old version is vulnerable because it tries to pull a pre-built binary from an S3 bucket, right? And well, now it returns 403, well, 403 because we control it right now. And not the plea is basically a wrapper around a native binary that will be installed on your machine from that S3 bucket, right? And we can just modify that library. We can add our code every time the library is loaded and, well, get code execution on the machine. And let me show how it works in practice, right? So again, so if we execute this not top plea package, right? So an old version, it's probably like 5 years old. You see the attempt 403. Yep. So it's trying to pull that archive and extract it on the machine. Right, so this is the name basically. And I have a version of it, slightly newer, just to make it easier to compile. But it's basically the same package, right? And vulnerable to the same problem. So let's change, again, the reference to the bucket to something without active clients. So we add just additional string, right? And now I already compiled the backdoored library and put it in the bucket, so to make it like the demo faster. All we need now is to, well, basically execute the package, right? So and if we execute it, so it tries to fetch a bunch of stuff, but at some point it will fetch the pre-built library and install it on the machine, right? So, okay, now at this point, the backdoored library is there, and if we execute the binary, we get arbitrary code execution. So yeah, pretty nice. Thank you. And the impact of this would be quite interesting. It would lead to installation of a backdoored library on 5 Fortune 500 companies, like including 3 largest banks in the world, AV vendor, a global telecom company, and a huge retail company, right? And there's another example called Kuvadev. This one is interesting because it references as a Maven additional host repository for this package that I have never heard about. But in the log, I found like 288 hosts pulling thousands of packages from that repository. This is an example of logs. And this would be also quite dangerous. It would lead to again, installation of backdoored packages on 5 government entities in Europe and South America, global investment fund, and 2 major like tech and telecom companies. We have limited time, so I cannot go through all examples of sensitive request types. I just want to quickly mention that I had a lot of requests to PHP and JavaScript. I also had requests to static like sensitive files and web pages. And most of them like PDF, docs, and well, Microsoft formats. You might be thinking, okay, Max, what's the problem with the static file format? And well, it's a good social engineering vector because you already have established trust with potential victim, right? So they come and download something on the website, and you can, well, it wouldn't be super odd to ask them to run some command, let's say in a PDF, like a manual, or in case of this weird engineering calculator, ask them to enable macros, right? And in this particular case, it would be like 3 state-level agencies in Europe and in South America, and like integration design firms, right? So it's relatively interesting vector. And what's funny, I had like data write attempts. So I created a bucket and I see people trying to put logs in my buckets, right? Which is quite quite funny in my opinion. But obviously I didn't enable. I don't know what they wanted to put into my buckets because it might be sensitive, right? Okay, let's go to the most like funny part, malware. Let's start with some statistics. We can see the stats are dominated by two families, RK and linker. Basically, they represent a huge chunk of all of the malware. But linker is malicious Chrome extension masquerading as a benign application in web store. For example, Flash playlist on the screenshot on the slide. And when victim visit some interesting websites, linker pulled JavaScript from S3 and injected it into the victim's browser, right? And the main purpose is to show ads. It was active like 3-4 years ago, but since then it was taken down from Chrome Web Store, and the author eventually abandoned it. But in the logs, you can still see a lot of requests to those buckets, like request, bucket name. What's important for us is referrer, right? It actually tells us the context in which like website this JavaScript will be executed, right? And there is even public research on that sample. And the extension just pull config from this flashplaylist.com, right? And the website should return this Mixpanel variable with the link to the bucket and JavaScript, right? Name. And the code is obfuscated, but all it does is basically install it in the Chrome local storage, and then this variable is used to pull the script anytime user visit web page, right? And well, since we control S3 bucket, we can put any JavaScript we want. Let me show you how it works in practice. So again, a clone of the S3 bucket with no active clients, malicious JavaScript, test bucket, just to show you, well, some data can be exfiltrated from the JavaScript, and this is a malicious extension installed in the browser, right? Let's just visit some websites to show how it works. Let's like Gmail, Twitter, Instagram, Facebook, LinkedIn, right? And you can see basically our JavaScript got executed on all of those websites, right? And you can take a look at logs, right, and see that there is actual attempt to pull the JavaScript from the bucket we control, right? And let me show that, well, it's possible to weaponize it on in some context, right? So, for example, on TikTok, you can actually exfiltrate some data. Well, Amazon is allowed in CSP policy on TikTok, so it's quite easy, right? So in the JavaScript, we take everything that's available to our JavaScript in the context and put it into the bucket, right? So obviously, you cannot like steal HTTP-only cookies and probably not all the data, but still, I mean, this is a question on how to weaponize XSS on all of these resources for the attacker, right? You can see like cookies, you can see page data. I want to rant about this captcha. It's just crazy. So I wanted to show you a test account from Microsoft, and I tried to register an account, and like I spent decent amount of time, probably the hardest challenge within the whole research, and it's crazy. This captcha is crazy. I couldn't, so no Microsoft demo for you. Like I didn't know how to move the person to the right place. I don't know. Well, this is impact, right? So thousands of users on like many websites like Google, YouTube, and Facebook, and so on. But obviously, there is nothing wrong with those websites. It's basically malicious Chrome extension that inject JavaScript. It has control over the browser, right? And I hope that naturally this extension will die, right, because of introduction of Manifest v3, and the extension depends on Manifest v2. We'll see. What about sensitive users? We have a lot of them. Again, a lot of people visiting like government websites in 30 countries, and actually people from government networks visiting government websites. So yeah, quite risky. RK. RK is malware pretending to be useful, like executable. It tries to steal your data. It was active like 4 years ago. It was forked by other families. That's how it looks in the logs, right? A machine-generated bucket name and the request to pull executable. And there are a bunch of old Joe sandbox reports indicating, okay, that actually happened. The problem is replicating this malware is quite challenging because you actually need to find the executable who would like pull from like S3 bucket, and it was hard because first of all anti-VM, anti-debugging, and second, well, malware is not active anymore. Part of its infrastructure is dead, so you cannot reproduce it in any way. But for you, I found the sample after like really long search. So RK Stealer. So we are in Windows VM. We have Wireshark. Installer is actually our malware, and we have FakeNet NG. I'll tell you why we need it. So let's start Wireshark just to see what's going on the wire, right? So then we run installer. We see some traffic, right? At this point, you are infected. Don't pay attention to all of this. This is fake. We can see the actual request, right? And it's HTTP, obviously, because, well, malware doesn't care about your security at all, right? So it tries to pull the executable over HTTP, right? This is the actual executable. And what you can do, actually, you can spin up FakeNet NG that will respond with executable to every request that malware makes, right? So it's like a fake server for malware. And in our case, we're going to serve it calculator. So now see what's going to happen. So we run malware, and ta-dam, we have our calculator, right? So now in FakeNet NG, you can see the actual request, right? It tries to probe whether the bucket is available and the executable is there, and then just download it over HTTP, right? And we just give it calculator, right? And it executes it blindly. All right, so that was RK. Now let's move towards total impact. This is an overall map of the users that I verified could have been compromised from this attack, right? It's 28,000 users, 158 countries, 134 organizations, and 25 government networks, right? And you might be thinking, well, Max, we saw bigger attacks, right? But I want to remind you, it's just 5 days of monitoring logs. Right? God knows what would happen if I would look for 2 months. Again, lazy hacker. Anyway, country statistics: US, Russia, China, Germany, and other European countries. Right? $20 the cost of attack. You can likely do it in zero budget that I spent on log storage. Right? And this is attacker profiles. As you can see from impact, that would be interesting from anyone, from hacktivists for fun to cybercrime for, well, cause financial damage, well, ransomware and stuff like that, to APT groups for sabotage and espionage purposes, right? And responsible disclosure is quite interesting here. As one person who helped me with this research pointed out, there is a paradox here. In order to find vulnerability, you have to fix vulnerability, because once you claim the bucket, it's not anymore vulnerability because the bucket is claimed, right? So, but still, I didn't want to sit on all of those buckets because, well, it's quite dangerous, right? So eventually, I collaborated with AWS on remediation campaign, and they sinkhole all the buckets that we identified as sensitive, right? Yeah, it was really a positive collaboration with them. But I want to highlight that this is likely a tip of an iceberg here, right? A sizable tip, but what about other package repository? What about GitHub commit history? Because source graph doesn't allow you to search in the commit history. What about proprietary code? And what about other cloud providers, right? AWS is just one example. Because of its size, I picked it, but there are others. And S3 buckets is just one problem, right? There are other type of abundant resources that an attacker can exploit, like dangling IP domain and domains and other stuff. So yeah. And if we ask any cloud provider, they would point out that it's basically customers' responsibility for, well, don't forget your code and references to dangling buckets, right? And unfortunately, I think they're right. We should not forget about the code, right? We should not forget about the references to the buckets that doesn't exist, that represent risk. And through the course of collaboration with AWS, they also wanted to share that it's also possible to rely on machine-generated bucket names in certain cases, or make them less predictable to reduce the risk here. And also they rolled out recently a higher cap for amount of buckets you can have, so per account. So per account, you can now have like 10,000 buckets, and well, it's a lot. You probably, like, it would probably incentivize people to, well, not delete buckets. Like, why do you need to delete it? Like, keep it, right? Yeah, so those are the references if you want to look deeper into that. And like blaming engineers is nice, right? But it's not productive. I would say it's counterproductive, and I believe that in general, as a security industry, we can do better, right? So if you work on like static source code analysis, or you're a code storage provider, or you're just within a security team within your organization, look for dangling buckets that reference to something that doesn't exist, and well, remove it. It's not that hard, and I wanted to release a tool to do it, but eventually I found a bunch of tools already exist for that. So just use one of them, and they're pretty decent and much better than I would write them. And the real root cause fix here would involve secure by default cloud, right? So it's either bucket namespace to be project scoped, right? So you have project name and bucket name, where project name is immutable. You cannot like delete and someone else reclaim it, or even better, like just make bucket names non-recyclable at all. So it's not possible to reclaim them, right? It's possible. Probably there are some caveats with abuse potential, right? Or general people claiming all cool buckets. Maybe, maybe not. It requires some research on critical user journeys, right? And as for buckets used by malware, I think the best path forward is just to keep them always private. There's even like this shadow server initiative that's in called domains used by malware. So we can, well, cloud providers, I think, can apply the same strategy for buckets, right? All right, I hope I convinced you that abandoned cloud buckets is a serious problem, right? You can run the attack with relatively low cost, and LLMs and elements of big data analysis can really bring this on like a gigantic scale, right? And well, help attacker reduce the time and effort required here. I would like to thank Electronic Frontier Foundation for help here, and a lot of amazing people who made this talk possible, as well James Erickson and overall Amazon security for very positive collaboration. They wanted to share that they are always welcome to collaborate with security researchers to make like the cloud and their customers more secure. Those are the references, and well, basically that's it. Thank you, and I'll be near the stage.